Yes, sir.
Yes, no? Early
Last
fact means
time,
last time I explained, no?
yes, sir.
Yes, yes. So today I'll start the transistor biasing. Candidates have only joined. Okay, let me start now. I think my screen is visible to you. Okay. What is biasing? Why we need biasing? There are three configuration of transistor: common base, common emitter, common collector. And generally, common emitter configuration was being used at the past because it was having moderate gain, and it was having high voltage and current gain and power gain, and so many properties are there. So that's why we were following the usage of common emitter configuration for being utilized as an amplifier. Okay, and after that. Uh, Okay, before going on transistor biasing, I'd like to explain select operating Q point. Operating point. Q send point. Already we had some question what is the Q point. Generally, this is the point where any device operates. Okay, so what is Q point? This is the level of voltage and current with which any device operates. All the participants are requested to keep themselves on mute. Okay, so this is the level of voltage and current with which any device operates. Suppose suppose I'm taking the common emitter configuration, I'm taking output characteristics. So generally for defining the Q point, we generally take the output characteristics. This is IC and this is VCE for common emitter configuration. And you remember that what is the meaning of common emitter configuration? Okay, a common emitter configuration means we apply here VDE, and this voltage is at output terminal VCE. Okay, and this is plus minus, and this is minus plus, and NP and NPN. So this is plus minus. Okay, so this is CE configuration, and these are the characteristics where I'm going. Saturation region, and here this shows the level of IV. Goes to 0 milliampere. 1, 2, 3, 4, 5. Okay, and here this is known as cutoff region, as you know well, and this whole region is known as active region. Okay, so generally we operate in active region. Transistor operates, okay, as an amplifier. So here I would dictate in active region transistor operates as an amplifier. In saturation region, it can act as switch, and in cutoff region does not operate. Okay, fine. So these are the basic terminologies. If we want any transistor like BJT to be working as an amplifier, so in that case we have to operate in the active region only. And if we just want to operate the switch with this any BJT transistor, then we have to go for saturation region. Okay. So there is one thing that is called DC load line. DC load line. Okay. Here what we do, we just draw a line like that that connects that IC. Maximum value of this IC remains ICC, and maximum value of VC remains VCC at this point. And this is called DC load line. And here at any point on this DC load line, we select the current. We can define the value of current and voltage. Okay, so DC load line defines value of voltage and current in transistor and defines whether transistor is working in cutoff region, active region, saturation region. So just think, if I select that, if I go in this on this point, so definitely if I define the characteristic of transistor at this point on DC load line, so I can say transistor will be working in the saturation region. And if I select the transistor's characteristics, point, voltage, and current at this point here on DC load line, so definitely this is an active region, and we can say transistor can work as an amplifier here. And now question is how to select the Q point. How to select Q point, and the point on DC load line is known as Q point because this is the level of voltage and current. Okay, Q point defines the level of voltage and current with which any device operates. So suppose I have selected Q point here somewhere in the middle of DC load line in active region. This is the coin. This is the very important question: how to select the Q point. Okay, so suppose I have selected Q point here in middle of the active region and approximately mid in the DC load line. So you just think what happens. Okay, I'm drawing some lines here. So I'll tell you how we can select the DC, the Q point, and on a particular point at the particular point on DC load line. So you see, if we just at this point, if I see the voltage waveform, if it is like that, okay, then definitely the current waveform will be like that. Fine. And here, this point, the maximum of this maximum on positive side and maximum negative side, this point is in active region, this point is in active region. It means this full signal will be, we are having full signal, and it will be achieved at the output, full signal. Now see, if I select this Q point somewhere at this point at upper side or Q point at the lower side, what will happen? So let me explain what will happen exactly. This is again transistor characteristics, and I'm going to select something different from the last version. Okay, so what we are doing, like suppose I have drawn a DC load line over there on the transistor characteristics, and I'm going to select this Q point here. This is not in mid of active region. This is somewhere at the upper side. This is Q point. So you see, if I just draw the lines, You see, if I define the region of operations, if this is saturation, this is active, and as usual, this is cutoff. Okay, so if I draw the waveforms, so you see at this point this is fine till here, everything is fine because this point is lying existing in the active region, and we are going to operate this transistor in active region. But this above this point, this transistor comes in the saturation region. So what will happen? The maximum peak, it will be clipped. It will be clipped. Okay, it will be clipped because this transistor comes in the saturation region beyond this point. In the similar manner, at beyond this point, this waveform may be clipped. Okay, fine. This point will be clipped. Okay, fine. So this is clipped. So you can think here, like if you are selecting Q point somewhere else other than the center position of this active region, then some portion of the waveform, output waveform, either voltage or current is clipped. And this is not required in any way for proper amplification. Now, the third case, I'm going to select this Q point somewhere at the lower position. Okay, I see this is VCE and this is PCC, this is ICC, and suppose I am going to select this point here somewhere at the lower position of the DC load line. This is Q point I have selected here. So what will happen? I can draw this lines again and I can do this exercise. So you see this cutoff region is now playing the important role. This maximum portion of this waveform is coming under the cutoff region. So again, what will happen if I draw the characteristics? Then this portion of this characteristics will be clipped due to the portion of waveform maxima or peak lies in the different region other than active. And here, okay, so let's why we select the Q point in mid of the active region for avoid clipping the waveform of voltage and current. Okay, so this is the reason. If somebody asks you why we have to Q point, so you can, I think it is very easy to explain how can you select the Q point, operating point of transistor. So if, and one more thing, this is very important, if you are going to work, if you utilize your transistor as an amplifier, then definitely Q point must be selected in mid of the active region somewhere. If you are going to utilize your transistor as switch, then definitely you must operate the transistor somewhere in the saturation region on the DC load line, and in the cutoff region, transistor does not work. Okay, so this was the basics, and it was very easy. And now another term, this is called biasing. What is biasing? BJT biasing is used to stabilize the Q point. Okay, biasing, why we go for biasing, why we use biasing? Because for stabilizing the Q point, we use the biasing. There are three types of biasing mainly. Number one, fixed bias. Second one, potential divider bias. or called this is self bias. Okay, and third one, collector to base bias. Fine, there are three types of biasing, and here I would explain first one, the fixed bias. What is that fixed bias? What we do biasing, like suppose I'm going to utilize common emitter on amplifier, common emitter configuration as an amplifiers. I'm just going to make an amplifier, and simply we know that we will utilize common emitter configuration in the amplifier. And now we have to stabilize the Q point. So we have to go for biasing. Okay, so this is simple common emitter configuration, and you see here we apply resistance here, we apply another resistance here. Okay, and this is plus BCC power supply we have applied here. Okay, and in common emitter configuration this is grounded as usual. This is called base resistance, this is called collector resistance, and here due to this power supply one current flows, it's called collector current. We get one another current that is called IB, base current. Okay, and definitely the voltage in the common emitter configuration, this voltage remains plus minus BBE, and this voltage remains plus minus BCE. Am I correct? This is simple common
Yes.
emitter. Yes, and only I have applied two resistances, one power supply, and this circuitry is known as fixed bias. Okay, fixed bias. So if somebody asks you what is fixed bias, we apply one resistance at base terminal, one resistance at collector terminal, and both are shorted to the power supply. And this is called fixed bias network. Okay, now I'll try to apply some KVL or KCL equations. So you can see here there are two loops. Okay, so one loop I'm going to utilize at minus PCC plus ICRC plus BCE equals to 0. Equation number 1. Now tell me what is the problem in this equation. Do anybody has some problem in this equation? Is there any difficulty in writing this equation? Yes or no?
No, sir.
Yes, sir. Yes, sir.
No,
Okay.
sir.
And still I'm saying if somebody is facing some problem in writing this equation, inform me right now, because this will be the basis for our till 4-year analysis throughout your engineering. Okay, if you are in the branch of electronics and communication engineering, if you do not understand or if you feel any difficulty, inform me right now. I'll tell you, I'll explain this in different way. Yes, that is fine, Mr. Indrajit. This is very good. You accepted your problem. So I will explain with the different way. Okay. So here, let me explain in this. Okay, I have applied this kind of circuitry. Fine. This is simple fixed bias network. Okay. And here I am applying one power supply like that. Plus minus BCC. This is RC. This is RB. Okay, already you know the voltage across these terminals. This is VBE plus minus in common emitter configuration, and voltage across these terminals, this is VCE plus minus. I think there is no problem now. So you can see here there is one loop this is one loop, okay, and this is another loop. You can see, okay, this is first loop, this is second loop. In first loop, if you will write equation, then minus BCC, and here this current is IC and this current is IB. So if you write minus BCC plus ICRC plus BCE equals to 0, this is first equation. Mr. Patel, is there any problem?
No, sir.
Yes. Now I think this is very clear.
Sir, I don't understand, sir, when circuit is not completed like this, it feels some difficult for me.
When circuit is not completed, like this one.
Not complete, not yes, not completed means like previous one only
This one,
written
this one.
full.
Yes, yes, yes. So you just do this kind of exercise. If this is not completed, if this is applied, I have mentioned here plus sign. You just try to complete this by extending this wire. This is simple a wire. This is a simple wire, and this is battery. I have extended this wire and I have connected this with the ground. Now it becomes very easy. Okay.
Okay, sir.
Now we will go for second loop. Now we'll go for second loop, and second loop says minus BCC and plus IBRB plus VBE equals to 0. This is second equation. Fine. So, okay, this will be very easy to understand if you will solve a numerical. So, we'll before going on another way, I would like to explain one. I would like to solve one numerical problem. Yes. Determine. Question is following for fixed bias configuration having RB equals to 240 kilo ohm, RC equals to 2.2 kilo ohm, and beta equals to 50. And what we have to determine? First one, IQ and ICQ. Second one, BCEQ. Third point you have to determine, that is BB and BC. And fourth point, BBC. Okay, so we know that what is fixed bias configuration. So first of all, we will draw fixed bias configuration here by ourselves if this is not given in question. And as we know that this is RB, this is RC, and in fixed bias configuration it will be power supply. And this one more thing is given, this is BCC, it is equals to 12 volt plus 12 volt. Okay, so now we can apply equation. First equation, plus BCC minus BCC. First this current will be there, another current IB will be there, okay, and this voltage will be there, this will be BBE, and this voltage will be there VCE plus minus, okay, minus VCC plus ICRC uh, plus VCE equals to 0. This is equation number 1. Can we put this value? Minus 12 plus IC into RC. RC is 2.2 into 10 raised to the power 3 plus VCE equals to 0. Equation number 1. Okay, that is one modified one. Okay, fine. And now we'll apply the KVL at another loop, plus minus VCC plus IBRB plus VB equals to 0. This is equation number 2, and here I am putting this value plus 2 and IB, and what is that value? 240 into 10 raised to the power 3 plus, what is the value of BBE? If transistor is working in active region, the value of BBE will be 0.7 volt. Keep this in your brain forever. If transistor is any region, if any junction is forward biased, in that case that voltage will be 0.7 voltage. Now I am saying that this is being utilized as an amplifier, and definitely this transistor will be working in active region. And if this transistor is in active region, then this input junction will be forward biased and output will be reverse biased. So if this is forward bias, then in that case VB will be 0.7 volt equals to 0. So here I am just writing one note. If any junction is forward bias, then minimum potential drop across it will be 0.7 volt. The minimum. Keep this in your brain. Okay, so as we know that this is working as an amplifier, and in amplifier, if any transistor is working as an amplifier, then definitely we know that this transistor must operate in active region, and for operating in active region, output junction must be forward bias, reverse bias, and input junction must be forward bias, and this is BB is the input junction in common emitter configuration. And if this is forward bias, then definitely this voltage drop is not given in question, so we will assume it as 0.7 volt. Do you understand this? I don't think there is any problem. Okay, so now everything is given here. So can I get this value of IB? Yes, definitely I can solve for IB. 12 minus 0.7 volt or 0.6 volt, I think. It's better to take it 0.6 volt. Or you can take it 0.7 volt. If it is not given, then you can take it 0.7 or 0.6, whatever. Okay, fine. And it is 240 into 10 raised to the power 3. So if you will calculate this, this will be 47.08 microampere, and this is IBQ. This is IBQ. Fine. So first term is done. Okay, and this is common emitter configuration, and we know that the relation for common emitter configuration, that is IC equals to beta IB plus 1 plus beta ICB not. Here reverse saturation current is not given in this scenario, so we will assume this is 0. this relation will be there. IC equals to beta IB. B IB we know, then we can calculate IC. Okay, so IC, and it will be ICQ, and it will become 2.35 milliampere. Fine. Yes. And then we'll go for the calculation of VC. That now here you see we know IC, IB, everything. Now we can go for equation number one. If we know this IC, then definitely we'll calculate VCE. That is second point. Fine. So from equation number two, we'll calculate VCE. So VCE will be 12 minus 2.35 multiplied by 2.2, and it will become 6.83 watt. This is VCQ. Now we have to calculate this point. This is very important. VB, VC, VB, VC, and VBC. You see, VBC equals to BB minus VC. Okay, and here since this is common emitter configuration, so emitter will be common. So VBC equals to VBE minus VCE. Here you see the voltage between this and this terminal. It will be VBE minus VCE. So we will calculate, and directly we can calculate. We can apply KVL here in this loop. Like if I assume this voltage is VBC, so you can apply KVL here, and you will find minus VBE plus VBC, and this will be minus plus BCE equals to 0. So it will become VBC equals to VBE minus BCE. Okay, if you will apply KVL along this whole loop. Fine. So now you know this value VBE, VBC equals to 0.7, and you know this value VC 6.83. Okay. And simply this says VB equals to VBE and VC equals to VCE, and VBC we can calculate. So now this third point and fourth point has been calculated. Is there any problem? I don't think that. There, that is called stability factor. Stability factor. What is that stability factor? Like generally, if we talk about stability factor, then what happens? Process of making transistor operating point independent of temperature or temperature variations. Okay, it is known as stabilization. And since he checked this line, this is very important line here. We are making transistors operating point free from the temperature variation. And you know what? If I'm talking about temperature variations from the diode, you know that there is one current that is temperature dependent, that is called reverse saturation current. Okay, in transistor that current is known as IC naught, ICB naught or ICE naught. Okay, this is temperature dependent current. So if we are saying that transistors operating point we are making temperature independent of temperature variation, it means we are in short we are saying that we are making transistors Q point independent of IC naught variations. Okay, so here like we know well, like stability factor we can define. There are 2 points. Operating point we are talking about Q point. Okay, Q point means we are talking about BCE and IC. BCE is always fixed, constant, but IC may vary. Okay, because we know that relation IC equals to beta IB plus 1 plus beta ICB naught or C naught. Okay, fine. So you see this IC will be the function of IC naught. Means you can see IC is the function of IC naught. And here you can say IC naught is the function of temperature. Understood? Means one thing, we are the process of making transistors operating point means transistors collector current independent of temperature variation means independent of reverse saturation current is known as stabilization. So we have decoded the meaning of this definition. Okay, and now we'll go for that. What is stability factor? So we have decoded this all. So what is the stability factor? IC should be kept constant in spite of variations of ICB naught or ICE naught. Okay, so this is called okay, and the rate of change of collector current in respect of reverse current is known as stability factor. Okay, what is that stability factor? I hope you understood. The rate of change of collector current in respect of reverse current, IC naught. Okay, reverse leakage current, reverse saturation current. Okay, that is known as at constant beta and IV stability factor. And one more term it must be added here, beta and IB. remain constant. This is very important. Let me explain. Like I'm having current IC to beta IB plus 1 plus beta IC naught. Okay, and if I differentiate this with respect to IC, del IC over del IC goes to beta del IB over del IC plus 1 plus beta del IC naught over del IC. Okay, and here this factor becomes 1, and now we can write it 1 minus del IB over del IC close to 1 plus beta del IC naught over del IC. Okay, and this factor specifically you can mention this factor del IC naught over del IC. This is if I am representing stability factor Ys. So S equals to, already know from definition, rate of change of collector current with respect to reverse leakage current is known as stability factor. This is the definition. The rate of change of collector current in respect to the reverse leakage current is known as stability factor, where V and IV remains constant. So mathematically I can write this stability factor like del IC over del IC naught. So this becomes 1 upon S. Okay, and here again we can rewrite this equation 1 minus beta del IB over del IC equals to 1 plus beta upon S, and here I can write the stability factor, that is 1 plus beta over 1 minus beta del IB over del IC. Okay, and why we are discussing here stability factor? Like stability factor, already we have decoded that the process of making transistors operating point independent of temperature variations, independent of IC naught. That's why we are we are discussing here stability factor. Okay, and if we are talking about stability factor, it means we are talking about operating points. If we are talking about operating point, then definitely we are talking about IC. And if we are talking about operating point, then in short, we are talking about biasing. There are three types of biasing already I have explained: fixed bias, potential divider, collector to phase. In all kind of biasing, stability factor will be different because these configurations are different. And Q point will be selected in different way because biasing, the way of biasing is different. That's why we are going for definition of that stability factor. So for fixed bias, if I define the stability factor, can you calculate the stability factor for fixed bias? 1 minus beta del IB over del IC. What is that equation at the input loop? This is the equation, this one. Can I get the del IB over del IC? I hope I can calculate the stability factor for fixed bias. Okay, we'll calculate the stability factor for each and every kind of biasing. But you keep this remain the this constant, this concept of stability factor. You keep this in your brain, and in the next lecture we'll explain what is the stability factor for different kind of biasing, and we'll study about different remaining biasing types of biasing. Okay, so if today, is there any problem today in this session?